Okay, this is the remaining problems from the section 4.1, 4.3/4.2 notes. This had to do with graphing polynomials with degrees of greater than 2, multiplicities, and long division. So the first example we need to go over is another variation of the intermediate value theorem. Remember that this theorem says that if you evaluate a function at two separate x values and one of the y values turns out positive and the other y value turns out negative, what that means is that somewhere between those two x values you have crossed the x-axis or you have a 0 for that function. So we did A in class, so that means that we need to continue with B. So if we evaluate this, we're going to do our two x's are 1/2 and 3/4, which are pretty close together because that's 0.5 and 0.75. So what we want to know is, do we cross the x-axis between those two? So if we plug in 1/2 for all of the x's in the function, we're going to work this out. So that's 2 times 1/16. That would be 3/2, just leave that as that. And then this would be 1/8. And then I'm going to get a common denominator of 8 for everything. So this would be 1/8. We would multiply this by 4/4. So that would be plus 12/8. And this times 8/8. So minus 16/8. So this comes out to 13 minus 16. So this is negative 3/8. So when we evaluate the function at 1/2, we get a negative value of 3/8. Now, the next thing we need to do is evaluate the function for 3/4 and see if that also comes out negative. If it does, then we don't know if we crossed the x-axis. But if it comes out positive for the y value, we know we did cross the x-axis. So 2 times 3/4 to the 4th power plus 3 times 3/4 minus 2. Still plugging it into our function. This would be 2, and that would be 81 over, let's see, 4 to the 4th, I believe it's 256, but we're going to double check that. Yep, 256. Plus, this would be 3 times 3, so that would be 9/4 minus 2. I can reduce the 2 and the 256. And then we will reduce that down. So 256 divided by 2 is 128. So this would be 81 over 128 plus 9/4 minus 2/1. And we want to get a common denominator of 128 if we can. So 128 divided by 4. We need to multiply this fraction by 32/32. And this one by 128 over 128. So this would be 81 over 128 plus 32 times 9 is 288 over 128. And 128 times 2 is 256 over 128. So if we add across the top, that is 81 plus 288 minus 256, which is 113 over 128. So yes, there is a 0 between 1/2 and 3/4. Since this was a negative y value and this was a positive y value, by the intermediate value theorem, we have crossed the x-axis between these two values. So that is what that theorem is all about. Okay, so let's look at what we have next to catch up on. We found the zeros of a polynomial, stated the multiplicity. We did that one in class. We talked about behaviors. So this is just more examples of graphing polynomials that have a degree higher than 2 and figuring out when are they above or below the x-axis. So let's look at this one right here, part B. We can pull out an x squared as a GCF because we're going to try to factor this first to find our zeros. That would leave me with x squared plus 3x minus 4. And then that factors again into x plus 4 and x minus 1. So I get 3 zeros here. X squared would be 0 if it was 0. X plus 4 would be 0 if it was a negative 4. And x minus 1 would be 0 if we had a positive 1. So that means we have 3 intercepts that are on the x-axis, 0, 0, negative 4, 0, and 1, 0. So we can go ahead and plot those over here. So 0, 0, negative 4, 0, and 1, 0. That one's really close to the other one. Now we're going to make a chart to figure out when are we above or below on the x-axis. So place these intercepts from least to greatest, so negative 4, then 0, and then 1. Write your intervals. This is negative infinity to negative 4, negative 4 to 0, 0 to 1, and 1 to infinity. Remember, we don't worry about brackets on these because we don't want to actually equal 0 for our final part. We're going to be looking for when are we above or below. The equal to 0 is these parts anyways. It's the columns. So then our test values, we need something smaller than negative 4, so negative 5. Something between negative 4 and 0, maybe negative 1. Between 0 and 1 is going to have to be a decimal, so 0.5. And bigger than 1, we can use 2. We place our factors. Now you can either write x squared here if you want, or you can write x and then another x, but it has to be taken care of. So this would be x, I'm just going to do it with x squared, x plus 4, and then x minus 1. And then we're going to find the signs of all of these. Now, if you square an x, you're going to get a positive every time, no matter what you plugged in. So negative 5 is going to be positive squared. When it gets squared, negative 1 will be positive when it's squared. So will both of these. So because this is squared and it's just plugging in the number and then squaring it, all of those come out positive. Negative 5 plus 4 is going to be negative. Negative 5 minus 1 is going to be negative. Two negatives multiplied together make a positive. Negative 1 plus 4 is positive. Negative 1 minus 1 is negative. One negative makes a negative overall. 0.5 plus 4 will be positive, but 0.5 minus 1 would be negative, so this is also going to be negative. Notice we get back-to-back negatives. That means there's going to be a bounce. We're going to touch the x-axis and go back. And that makes sense because that is a multiplicity of 2 on that 0, because 0 came from x squared. And then 2 plus 4 is positive, 2 minus 1 is positive, 3 positives multiply to a positive. So what this helps us see is what the graph is doing. Remember, these are my x-intercepts right here, these guys. So on the left of this first x-intercept, I'm up. In between the next intercept and this one, I'm below. So I go down some unknown amount and then start heading back towards that point. This tells me I stay below, so I bounce off of this and go back down. We don't know how far, and we don't really care. We're just getting a generic shape. And then on the last intercept, after we pass it, we go back up. So this is our generic shape of this polynomial. So notice that this is all we're looking for. We don't care how low these peaks get down here, or these valleys. Then the next piece that they always ask for, and this will show up on the test too as a blank, is they ask when was f of x greater than 0 and when was f of x less than 0. If you've done your chart, you have that answer right here. You just have to look at the pluses as being greater than 0, and this was supposed to be an infinity, by the way. I don't know why that looks like an 8. And then the minuses would be the less than 0. So from negative infinity to negative 4, unioned with 1 to infinity, that's when we were above the x-axis. From negative 4 to 0, and then from 0 to 1, that's when we were below the x-axis. Okay, looking for another example, let's look at part E. So in part E, we need to factor this again. We probably need to pull out a negative first to make this easier to factor. So I'm going to pull out a negative 1. That will affect my chart when I go to do it. This is now x to the fourth minus 12x squared plus 27. And we need factors that multiply to make positive 27 but add to negative 12. So it looks like, and this will be an x squared and an x squared since it's an x to the fourth. Looks like it'll be a negative 9 and a negative 3. So then when we factor those, this turns into two perfect squares because x plus 3, x minus 3. This is not factorable because it's not two perfect squares, but we will be able to get x-intercepts out of it. So my x-intercepts, remember you said anything that has an x equal to 0 and solve it. So this one is negative 3, positive 3, and then this actually ends up being a square root problem. So we get plus or minus square root of 3. So notice we get 4 separate x-intercepts because of that x squared minus 3. So my x-intercepts are negative 3, 0, 3, 0, negative square root of 3, 0, and positive square root of 3, 0. We need to know what the square root of 3 is kind of as a decimal, just so we have a reference for that. So it's about 1.7-ish. And that'll be the same thing here. It'll be about negative 1.7. So notice the negative 1 does not give me an x-intercept though because there's no x there. So I need to plot these. So negative 3, negative 1.7, positive 1.7, and positive 3. We do our chart. Place these in order from least to greatest. So negative 3, negative square root of 3, positive square root of 3, and 3. My intervals will be negative infinity to negative 3, negative 3 to negative square root of 3, negative square root of 3 to square root of 3, square root of 3 to 3, and 3 to infinity. Test values, negative 4, negative 2 would be a good one, 0, positive 2, and positive 4. My factors, I do have to include the negative 1 here because remember it is affecting the sign of this overall polynomial. But the good thing is you just give it its own row and you just write that it always is negative. Negative 1 doesn't have an x attached to it, therefore it has to stay itself. X plus 3, x minus 3, and then x squared minus 3. There are all my factors. So negative 4 plus 3 would be negative. Negative 4 minus 3 would be negative. Negative 4 squared is 16, minus 3 is actually a positive. So 3 negatives in that column make a negative overall. So this guy is negative. Negative 2 plus 3 is positive. Negative 2 minus 3 is negative. Negative 2 squared is 4. 4 minus 3 is positive. 2 negatives make a positive. 0 comes out easy. This will be positive, minus, and minus. So 3 negatives make a negative. 2 would be positive, minus, and positive. So 2 negatives make a positive. And 4 would be plus, plus, and plus. But because of the one negative up top, it is negative. So notice I get negative, positive, negative, positive, negative. That means below, above, below, above, below. So we start off below, then we go above, then we go below, then we go above, then we go below. So below, above, below, above, below. And then my f of x part. For f of x greater than 0, you're looking for the plus signs. So that would be negative 3 to negative square root of 3, unioned with square root of 3 to 3. And f of x is less than 0, would be negative infinity to negative 3, unioned with negative square root of 3 to square root of 3, unioned with 3 to infinity. So notice that's just corresponding to when are you above and when are you below. Okay, so then I believe F was done in class. So we're now down to the long division. We did a couple of these together in class. We're going to try to finish up the ones that are left on the video. So starting with B, trying to divide 2x squared plus x into this long polynomial here. So we start off by writing the 2x squared plus x out front. When you write the part that's supposed to go inside, make sure each power has been represented from the highest all the way down to none. If not, you would need a placeholder. Now the reason we didn't do this one in class is because it actually comes out with some nasty fractions. So we have to talk about this because 2 does not go into 3 evenly. If you need something to multiply to give you a number that it doesn't go into evenly, there's a trick. You multiply by the number you want on top and the part you want to go away on bottom. So notice this is 3/2 because 2 times 3/2, the 2's would cancel and just leave me with a 3. Now I also need my x squared to turn into an x to the third. So I'm going to multiply by another x. So actually I need to move that down one more column because I like to line it up with the like terms. So 3/2 x. So we multiply what's here times everything out front. So that would be 6 over 2, which would be 3x cubed. And then 3/2 times x, 3/2 x times x, sorry, it's hard to say, would be positive 3/2 x squared. Then remember, because this is long division, we change the signs. So this cancels. We would need to do -5 over 1 plus -3 over 2. We have to do scratch work to add that. So this would be -10 over 2. So -10 over 2 plus -3 over 2 would be -13 over 2 x. So then when we combine our, sorry, I wrote that in the wrong spot. Goes underneath this over here. So -13 over 2 x squared. Bring down everything else. So -4x and -8. Okay, now we need to multiply this by something to make -13 over 2. Again, we want a -13 to pop out, but we can't just put a 2 on the bottom because this already has a 2. So we would need to multiply by 4. Now let me explain how that's going to work. So 2 times -13 over 4. We had to go bigger on the bottom because we already want a 2 in the bottom. So this would reduce down and leave me that 2 I need in the bottom. Now we don't normally give you anything with fractions like this on the test because for long division because that would be very complicated, but you do need to see this just to see how it works out. So then if we multiply this would be -13 over 2x squared. Then we multiply it by the x, so that's -13 over 4x. And then remember, because this is division, we change our signs. That's going to cancel. I'm going to use -4 over 1 plus 13 over 4. Get a common denominator. So that's -16 over 4 plus 13 over 4. That's going to make this -3 over 4 x minus 8. So it's not a pretty answer, but at least we were able to work it out. So the quotient is 3/2 x minus 13 over 4, and the remainder for this one is -3/4 x minus 8. I didn't write this one using the division algorithm because it's a little bit weird with all the fractions popping up. So that's the quotient and that's the remainder. Okay, so then we need to look at, because we talked about how this one is no solution, 0, we can't go. You can't divide a higher power into a smaller power, so just can't do that one. And then this one is my last one, so we need to do x squared minus x, at least for the long division, plus 10 into 7x squared plus 3x minus 10. X goes into 7x squared 7 times exactly. We multiply that by everything out front, so that'd be 7x squared minus 7x plus 70, and then we have to change our signs of that row so that we can subtract. This would be 10x minus 80. Now, x squared can't go into 10x because now this power is smaller, so that means we're done. So the quotient for this one is 7. The remainder is 10x minus 80. If we were to write that as a mixed number, essentially that would be 7 plus 10x minus 80 over the 7x, or excuse me, x squared minus x minus 10 by the part we divided by. So x squared minus x plus 10. So that's how that would look written in the fraction form. Okay, so this is just making sure we know how to use the remainder theorem, and we've been practicing this in class since then. But if you want to know, so say this was x minus 3. X minus 3 was what I was trying to divide by. Instead of dividing by x minus 3 and using long division, if you solve that over, it would be x equals 3. Think about it being equal to 0. If we plug 3 into the function and just evaluate it, that will actually give you the remainder for that function at this factor. So then you don't have, if all you care about is the remainder, you don't have to do all the long division. So f of 3 equals 2 times 3 cubed plus 4 times 3 squared minus 3 times 3 minus 1. That would be 2 times 27 plus 4 times 9 minus 9 minus 1. That would be 54 plus 45, or sorry, 36. Can't multiply in my head. Plus 36 minus 9 minus 1. Keep working. This would be 90 minus 10, or a remainder of 80. And that is the end of this packet.